Question 92 from chapter 2. Consider a large plane wall of thickness L with a surface at x equals 0 is insulated. So the x equals L is maintained at temperature 30 degrees Celsius. So the first thing that I usually do is if there is no picture, I try to visualize it. And I do that by actually drawing what I think, right? So this is the wall, and I will say that this is the insulated part. So this is x equals 0, x equals L, which is 0.05 meter or 5 centimeter, the thickness of the wall. And what do we have? Thermal conductivity of the wall is K equals 30. So K equals 30. Heat is generated in the wall at a rate given, okay? And they also gave us the E dot gen. So I assume one-dimensional steady state heat transfer, express the differential equation, obtain the relationship for the variation of temperature, and determine the temperature at the insulated surface. So now that we have a visual representation of the system, we're going to write down everything that we know, okay? So we know that E gen is 8 times 10 to the 6, and E dot gen is E dot 0, E dot negative 0.5 XL. Okay, all right, so that's all the information that we have for this problem. And again, just like the previous problem, we know that if there is heat being generated inside this thing, yeah, if heat is being generated in this side, no heat can escape, so the heat flux is 0 on the left side, and on the right side we have but they're saying that heat is maintained, so T equals 30 degrees Celsius, while the surface is maintained at temperature. So this is TL, right? TL, which is maintained at 30 degrees Celsius. So that's two important information. And we know that heat is going to be like this, right? Where this at T0, we're going to have a higher value at compared to TL. So knowing the boundary condition, let's go ahead and solve this problem. We have for E dot gen, that's what we have, okay? So that's what we have for E dot gen, and at x equals 0, E dot gen equals E dot 0, and 0.5 times x divided by L is just 0, right? And e to the 0 is 1. So E dot gen is E dot 0, which is 8 times 10 to the 6. That's the value that we have for E dot 0. So that's it for that. And then we also know that dx at x equals 0 is simply 0 because of insulation. And at TL, it's 30 degrees Celsius. So we're going to write the general form of the differential equation for a wall with heat generation. E dot gen equals K equals 0. And if we integrate this once, but before we do that, because in E dot gen we have this x term, right? We cannot just integrate it, take E dot gen as a constant. We have to integrate E dot gen as well. So d squared t over dx squared minus E dot 0, E dot 0.5, because we're doing x equals L, okay? Because we already know that x equals 0, that's what we have. And that x equals L, what do we have? That's why we're doing this equation. So E dot 0, E 0.5 divided by 0.05 is just 10, and then k. So e dot 0, e dot negative 10k, and then we're going to integrate this once. So d over dx equals e dot 0 is a constant, and so is k, e dot negative 10x dx. Okay, so we can use u substitution to say u is negative 10x, du is negative 10 dx, okay, and dt over dx equals e dot 0 over k, and e dot u dx, which is negative 1 over 10 du, which this will give us dt over dx equals e dot 0 10k eu, which is e to the negative 10x. That's it, okay, and then plus of course c1. That's our first integration that we have, and if we integrate this once more using the same technique, we end up with this. So we know that at x equals 0, dt over dx is 0. So let's copy this one here. So at x equals 0, this is 0, e to the 0 is 1, and 1 times that is that value, and this is 0, so it just means that c1 is basically so c1 is basically this is a negative, is it? Hold on, never mind, it's not a negative. Okay, so c1 is negative e dot 0, which is 8 times 10 to the 6 divided by 10 k, which is 30, and this gives us a c1 value of negative 266. So that's our first constant, and we know that at x equals L, our TL is 30, so we can use this equation. To find C2 directly. So this is 30. We know value of C1, so value of C1, which is 26667, x, which is L. I'm just gonna keep it like that for now, and then this is also just L. We know the value of e dot 0, we know the value of 100k, so this gives us a C2 value of that's our C2. So we have the two constants now, and once we have the constant, the last part is basically finding the temperature at T0. Okay, so x equals 0, and if we say that x equals 0 and we so if we say that x equals 0 because that's what we are asked for, so replace that with t0, x equals 0, so this term just becomes 1, and then c1 just goes away. We know c2 2980, so if we're just left with t0 equals negative e dot 0 over 100k plus c2. We know this, we know that, so t at 0 is basically 314 degrees Celsius. That's it. So as we said initially, t at 0 is higher, has a higher temperature than T at L.